Okay, so this is chapter 39 of our Astro 7 class, and I'm going to be summarizing in a fairly short show the key evidence that current global warming is indeed real and human caused. So I've got 13 lines of evidence that I can show you. And some of the studies and graphs that you'll see, many of them are, you'll notice, old. They date back 10 or even 15 years now. And I thought about, well, maybe I should update those. And I thought, no, let's actually leave them because I want to show that we've known for a very long time that global warming is real, it's human caused, it's not something new, and the protestations of climate denialists have been known to be empty for a very long time. So here's key evidence number one: a warming troposphere and yet a cooling stratosphere. So CO2, of course, you've all heard, will cause warming in the troposphere where we all live, but a cooling stratosphere at the same time. The very same CO2 that warms the troposphere should cool the stratosphere. It's a unique signature of rising greenhouse gases. Unique. And many scientists consider it the number one most convincing fingerprint, which global warming is human and is due to our own CO2. Okay, we're going to see later that the CO2 that's out there is overwhelmingly our CO2. Let's see now why a warming troposphere but a cooling stratosphere is exactly what you would expect. So we have two major influences on the stratosphere, humans do, and that is CO2 and ozone. So ozone absorbs solar ultraviolet light, especially the UVC and UVB. The harsher, the more energetic of the solar UV. And it breaks apart the ozone, which is oxygen 3, and in the process it heats the stratosphere. So this is a heating source to the middle upper layers of the stratosphere. There's kind of a sweet spot where if you go above the stratosphere, there's plenty of UV, but the oxygen density, the ozone density, is so low that there's not significant heating. And if you go below the sweet layer, then you have already used up most of the ultraviolet. And even though there's plenty of ozone, there's not enough ultraviolet left because it's all been absorbed at layers a little bit above. So it's a layer kind of in the middle upper part of the stratosphere. Mostly the upper part. Now, so ozone, though, was destroyed in significant part by chlorofluorocarbons. So these were refrigerants that were made, and the chlorine induces feedback with the chemistry of the ozone, and one chlorine atom can destroy hundreds and hundreds of ozone molecules. And when we finally understood this, we passed the Montreal Accords and we banned CFCs in 1989. And we've seen since then ozone levels have been very slowly but surely have been rising since then. So that's a good thing. We still have the ozone hole over the poles, but it's not quite as dramatic as it was. So how does rising stratospheric CO2 act as a coolant? So here's the way that works. The stratosphere sees less upgoing radiation because it's trapped by the troposphere, global warming. The upgoing infrared is absorbed to some extent by the rising CO2 at the bottom. But higher CO2 levels mean more frequent CO2 collisions in the stratosphere, and that causes molecular collisional excitation. So we remember from our chapter 5 how the molecules of any kind of molecules have these internal degrees of freedom, these internal motions where they can vibrate. And the more complex the molecule, then the more complex the different modes are. You can have many different modes, and in fact it adds up very quickly. So that if you just have a diatomic molecule like oxygen or nitrogen, a symmetric diatomic molecule, then you you actually aren't going to do more than just the vibrations back and forth, one single mode. And because the center of the electric distribution doesn't change for a symmetric diatomic molecule, even though it is a molecule, it won't act as a greenhouse gas. But if you make up your molecule of dissimilar atoms, so they have different weights, then the center of charge will oscillate back and forth with these different vibrational modes, and that allows it to absorb infrared light coming from really from any direction. So when you collide molecules together, then you can excite these motions. So remember that temperature is 1/2 mv squared equals 3/2 kT, and so the velocity of the molecule as a whole is what is measured by temperature. And when you have a collision, but some of that collisional energy goes into exciting these internal modes, then the rebound of those molecules off of each other is going to be slower. Basically, you have cooled the atmosphere, cooled the molecules, lowered their velocities, and stored that energy now in internal modes. So that's the first part. Here's molecules. They have these internal motions. This is water, one of the modes of water. And with all the collisions that are going on up there, then you can excite these internal modes. Okay? Now, what happens, though, is when the internal modes are excited, then they will tend to de-excite. When you take an atom or a molecule and put it into an excited state, then it won't stay there forever, typically. It will de-excite. And when it de-excites, it will give off a photon, give off an electromagnetic wave. Because of the energy levels that we're talking about, these internal modes, they're lower energy modes, this will be an infrared photon. Now, here's the key. The stratosphere is really, really low density, and therefore that infrared photon has a very good chance of escaping to outer space. And that means you've taken the energy measured by temperature from the velocity of the collision of those molecules, turned it into internal motion, and then dumped that internal motion into a photon, which now has a high probability of escaping. So this is a net coolant to the stratosphere. So you might wonder, well, gee, that doesn't sound so unique to the stratosphere. Why doesn't that happen in the troposphere, the denser part of the atmosphere where we all live? And it does. But the problem is that in the troposphere, the density of the air is so high, and the density especially of the water vapor and the CO2 and the other greenhouse gases is so high that now the odds of that infrared photon that you have created by de-exciting those greenhouse molecules now has a much lower chance of getting out. It has a higher chance instead of just getting absorbed by another greenhouse molecule. And of course, each time that photon is generated, it's got a 50-50 chance of heading down, another chance to hit the ground and just heat the ground. So where the air is dense, greenhouse gases tend to be an inhibitor to the outgoing heat. They tend to be an addition to the thermal resistivity, as it were, of the atmosphere. But where the density is very, very low, and the ability of the infrared photons to escape, therefore, is very high, then they tend to act as a coolant. Okay, so this is a characteristic physical process of greenhouse gases. So here's global ozone change, and you can see how global ozone was more or less constant here, and then we really started losing a lot of it as we generated a lot more of these CFCs, and we realized how dangerous this was, and in 1989 we passed the Montreal Accords. Ozone continued to go down for a little bit more. Since then, it's been gradually recovering. However, there are still illegal CFCs that are being produced, even though they were banned in 1989. So we don't really expect full recovery of ozone in the stratosphere until, another 50 years from now, perhaps. So what do we actually see? Do we see a cooling stratosphere? And the answer is yes. So this is the trend. Now you see a heating stratosphere when there's big volcanic eruptions that are powerful enough to send hot dust into the stratosphere. So there's Mount Agung in 1963. There's Mount Pinatubo in 1992. El Chicon in 1982. And now we've continued our cooling, even though ozone now is back on the increase. So even though ozone, which is a heater to the stratosphere, still the stratosphere is trending to cool. Now it's not as strong as it was before because ozone levels are going up. But if you had static ozone levels, then you would expect, and that's what we had, recall, in that earlier graph in this general area, and yet still we see a cooling stratosphere. So well-mixed greenhouse gases, they mix through the troposphere and the stratosphere both. They act to cool the stratosphere more than due to the loss of ozone. So the combined effect was more than a doubling of the cooling rate, and that's the red curve here. So it's kind of a complicated curve because we're talking about a rate down at the bottom here, degrees centigrade per decade. And then this is the ozone trend, and this is the ozone with other greenhouse gases in the red curve. Now this is warming in the mid to upper troposphere. So when you get into the troposphere, now it's dense enough that we still have warming due to rising CO2. But in the stratosphere, the density is low enough that the infrared photons have a good chance of just escaping, and we see a cooling. Okay, so that was all evidence number one. Here's evidence number two. We know CO2 is a powerful greenhouse gas. Plain old straightforward physics. You can verify it in the lab. Take a enclosed bottle of CO2 and pass infrared radiation through it and measure the radiation that you get on the backside. And you'll see these big absorption lines, okay? So CO2 has this big fat absorption line, and it is right at the peak of the outgoing infrared from the Earth. So take a black body radiating object like the Earth at 294 Kelvin. That's about, the average temperature of the Earth. It's about 55 or 60 or something degrees Fahrenheit. And this is what the Earth wants to radiate back out into space, the red curve. It's not able to do it because of greenhouse gases. And what are those greenhouse gases? Water vapor, methane, nitrous oxide, ozone. This is ozone in the troposphere that's problematic. It's a greenhouse warmant down there. Coolant up in the stratosphere. This is a little complicated, of course, because of the different densities. And then CO2 is the big one here. A little more nitrous oxide there, and a lot of water vapor here. Water vapor actually tends to blanket over a large part of this, and water vapor net is a stronger greenhouse gas than is the CO2. Sometimes you'll hear climate denialists try to claim that, it's not the CO2 that's the problem, it's water vapor. Water vapor is the real problem. Yeah, water vapor is a slightly bigger problem than the CO2 in terms of how much warming it does. But here's the thing. Okay, the water vapor is in contact with the atmosphere because 70% of the Earth's surface is covered with water. And water will rain out. So there's no way that you can simply decide that, let's just raise the humidity of the atmosphere, because it won't do it. You're trying to raise the humidity of the atmosphere, and if you don't have an ability to hold that heat in further, then it will just rain back out. So what you need is something that won't rain out, namely CO2 and nitrous oxide and methane. And those, as those go up, then they warm the atmosphere and they raise the humidity, and then it's the raised humidity that worsens the water vapor absorption of outgoing infrared here and here. So it's still the CO2. Okay, evidence number three, the rising altitude of the tropopause. So we remember when we looked at the structure of the Earth's atmosphere, the tropopause is defined by the region from the ground where the temperature drops as you go up, and then at a certain point it stops dropping, and then we have what's called the tropopause, and then above that the temperature actually rises as you go further, and that's the definition of the stratosphere. And the reason, recall, was because the stratosphere is warmed from above by the absorption of ultraviolet from the sun. The ground, the troposphere, is warmed from the ground by visible light from the sun hitting the ground and warming the ground. Okay, so where those two opposite temperature trends meet and pause is called the tropopause. So if we are warming the stratosphere and yet we are cooling, we're warming the troposphere and we're cooling the stratosphere, then you would expect that the tropopause would go up. And indeed, observations show it has gone up. It's gone up by about 200 meters during the 20th century. Now this is in pressure here, but pressure has a direct correlation with altitude, so they're both really the same thing. And you can see the trend here that they go up. And whenever you have a big volcanic eruption, like we had a number of them in the late 20th century, then you get a momentary reversal, but it doesn't last more than a year or two before those volcanic aerosols fall back out. Let's go back here, except for one study which showed a mild contribution of warming. The other 5 studies all show a net cooling. And in fact, that's easy to understand because during the last 60 years, the sun, as we're going to see, has been cooling. The sun's luminosity has been gradually going down. And then the other key thing that we can note is the astronomical cooling. We're at the bottom here in the last few centuries, and going for the next few centuries forward, we're at the bottom of a Milankovitch cycle, which induces a cooling. Okay, evidence number 5. What you'd expect if it's greenhouse gases that is causing the problem is you'd expect nighttime temperatures to rise faster than daytime temperatures. And the reason for that is because nighttime temperatures are inhibited from cooling because of the rising greenhouse gases. So remember, the incoming sunlight is not what's changing. What's changing is the ability of the Earth to cool. And the ability of the Earth to cool is, the Earth is going to try to cool at a maximum when you're in late afternoon. That's when surface temperatures tend to be largest and you're not being beat on by the sun quite as much. So that's when we try to cool, but we're not as able to cool because the inhibitor is not the incoming heat from the sun, it's the outgoing heat in the infrared from the Earth. And so what this plot is showing is that the daily temperature range for these different studies is all below 0. So here's 0, and they're all below 0. So we're warming, and yet the daily temperature range is decreasing. So that's another way, simple math will show you that, well, then the nighttime temperatures must be rising faster than the daytime temperatures, so that the total range between maximum daytime and maximum, or coolest at night, is below 0, as all this data shows. Okay, another way to show it, frequency of warm nights going up, up, up. Frequency of warm days, it's also going up, but not as dramatically. I think you can see these graphs are much more significant, these bars rather than these bars, which is the warm days. Infrared, and that's what this graph was about. But this graph is now measurements taken from the ground, looking up at our atmosphere and seeing how much of the outgoing infrared that we're trying to squeeze out is actually just getting reflected right back at us. So that's the meaning of this. And you can see that when you add it up, the model flux increase that we get from our computer models and the measured flux increase, actually the measured increase is even worse than the model fluxes, and that's always been a problem, is that climate models, they certainly tell us that we're causing greenhouse warming, but they continue to do they underestimate how bad it is. Evidence number 8, climate modeling agrees with observations for the distant past, so this only goes up to 2000, but only when you include human-caused effects. So we get a nice agreement down here when you include rising greenhouse gases, but when you take out the human influences, then the observational data, here's the black, that's the observational data, doesn't agree at all with what the climate models say we should be getting. Climate models say there should be a very mild decrease in temperatures, and we're not, we're getting an increase. So the overall trend is determined by human forcings, and that comes from CO2 and knock-on effect from amplifying water vapor, other greenhouse gases, deforestation, and so forth. And the forcings and the temperature actually agree pretty well, and what's really interesting is how even the bumps here, when you include volcanoes, they show up nicely. Agree very well. So the underlying natural variations in temperature, the colored lines, and supposed to go up. They agree quite well with all forcings predictions going at least up to 2020, or excuse me, 2000. Okay, evidence number 9. Plants preferentially take up carbon-12. It's a lighter isotope of carbon, and so it undergoes chemistry easier. And so there's carbon-12, and then there's a small amount of carbon-13 as a natural part of our atmosphere. But the plants preferentially take up the carbon-12, and that's what they then include into the fossil plants and animals that ended up becoming coal and oil and natural gas. And so they preserve that excess carbon-12 ratio, and then when we burn it, then we release that into the atmosphere, and we know that CO2 levels in the atmosphere are almost 50% higher than they were during pre-industrial, and so we would expect that to show up in the carbon-12 to carbon-13 ratio. And indeed it does. So that's what this graph is showing. So this goes back 1,000 years. We do have data on the ancient atmosphere by getting bubbles from ice cores, air bubbles from ice cores that go back 1,000 years easily. And so this is pretty constant for quite a while, and we discovered coal, and we started burning coal in the late 1700s, 1800s, and then we discovered oil in the late 1800s, and of course civilization took off and the burning increased incredibly. So what we're seeing here, it's a little hard to read the graph, this is the differential amount of carbon-13, and this is a negative number, and the negative number is getting more negative. So what this graph is showing you is that the amount of carbon-13 as a fraction is going down, down, down. It's going down at an accelerating rate, exactly as you'd predict. So this is proof that the CO2 that we're seeing in the atmosphere is not volcanoes, it's not, I don't know, whatever else the climate denialists will try and tell you. It's ours, okay? This is plant-based organic CO2 from fossil fuels. As human emissions rise, the atmospheric carbon-13 to carbon-12 ratio closely follows the emission trends. So here's both of them plotted together, and you can see that even the wiggles are preserved pretty much. They don't have error bars on here, but of course there is error bars in all measurements, and I think if you include those, you'd see that these are, very much consistent. Evidence number 10, we're burning carbon and we're generating atmospheric 2 at rates that are even higher than the atmosphere's CO2 rise rate. So you might say, well, gee, Rick, that's a lot of CO2 in the atmosphere. Are you sure it's really all ours? Are we really doing that much? Oh, absolutely, we're doing that much. We're doing more, in fact. This is the actual CO2 being burned. And that is actually steeper and higher than is the atmospheric CO2. that we measure. And of course, we learned why that was. It's because some of the CO2 dissolves into the ocean, and some of it is taken up by land plants and trees and so forth. And so only about 50% of the CO2 that we emit stays long term in the atmosphere. And we know the fossil fuel emission rates because we have data from industry. And so it's pretty obvious, huge expansion here as global economies ramp up, and doesn't show 2000 beyond 2000 here, but these go up much more steeply after 2000 because that was when China and the rest of Asia really kind of left the dark ages and became the fastest growing economies in the world. And all of it pretty much was fueled by coal and by fossil fuels. So evidence number 11, it's not just global totals, but the exact source on the global map shows it mostly comes from fossil fuel heavy countries. Okay, so this is the orbiting carbon observatory. It gives a unprecedented accuracy in the CO2 emission sources. So here's a map. And now, first of all, before you get too excited about the colors, we do have to show that CO2 really is a well-mixed greenhouse gas, and the numbers at the bottom, I know they're hard to read, but that's 388 is a mole fraction. That's 394, 395. So that's only 7 parts out of 400 roughly. Let's call it 8 out of 400. So that's only 2% difference, less than 2% difference between the CO2 least areas like the Amazon and the CO2 most areas like North America. So what's the takeaway here? CO2 is generated by America and Europe and Middle East, and then the prevailing surface winds will blow that north. And so we get it up here. There's also, of course, some CO2 being emitted increasingly from the Arctic permafrost. And there's hardly anything going on down here. No permafrost, no people. It's all very consistent. CO2 emission rates are still increasing, and so is the atmospheric concentration. Okay, evidence number 12. Fossil fuel burning depletes oxygen. And indeed, the oxygen level in the atmosphere is going down. So take carbon, combine it, burn it, you deplete oxygen. You deplete oxygen more than you would if you weren't burning all that carbon. So compared to what the ecosystems were used to producing in the way of oxygen, there's a deficit here. And there's 2 different hemispheres here, and that's why the curves show the seasonal oscillation, but they're out of phase from each other. And then there's a seasonal in the CO2 levels as well. This graph only goes back to 2006, and therefore only goes up to 380 parts per million. But here in 2020, we're so far off the graph I can't even show it. We're at 415 parts per million. And there it is again, CO2 going up, oxygen going down. This is from 2 very different places, one in Norway and one in Antarctica. So you see opposite seasonal effects, but they both show the same thing. Oxygen levels are going down. Evidence number 13, the growth rate of CO2 concentrations in the atmosphere drops during economic recessions. So these bars, that one and that one, these are just 10-year averages, and I kind of wish they hadn't put those in. I grabbed this graph from NOAA, and then I put in by hand these timings of economic recessions. So there's a 1960 recession, and we had a small decrease there. 69, 70 recession, again a decrease during and after that. This is the Arab oil boycott, OPEC, and 73, 75 recessions. 80-82 recessions. That was two rather strong recessions, one right after the other. Pretty strong decline there. Big decline here. This is the Gulf Oil War. And then the so-called Great Recession, though, wasn't really about oil. And while there's a decrease, it's not strong. It only goes up to 2011. But I believe we saw the same thing in 2016 when China had a near recession. And the recession that we're in right now, 2020, I'm sure it's going to show up pretty strongly. So those are all the 8 lines of evidence that show that global warming is real. It's caused by greenhouse gases, primarily CO2, and that the CO2 is unquestionably our CO2. Volcanic CO2 is less than 1% of the amount, year by year, on average, of what we put in by our fossil fuel burning. So here's what it's not due to. It's not due to the sun. So here's the temperature anomaly due to the sun in yellow. And in fact, if you look carefully, you'll see that the peaks here actually go down. And this only goes out to 2014, but we have gone through a very deep solar minimum, and we're still in it now. And this has only continued in the same direction, and yet global warming has actually accelerated quite a bit. So global temperatures is this curve here, accelerating upward. It's certainly not due to the sun. Could the sun be implicated in longer-term climate heating? Okay, so this is actually a really interesting paper that didn't get as much attention as I think it deserved, by Clete et al. In 2015. So we have seen for a long period of time that the sunspot number is correlated with the solar luminosity. We now have satellites that have been up there for 4 solar cycles, and they have seen a clear correlation. And so more sunspots actually equals more solar luminosity. Might sound a little strange, thinking of sunspots as dark areas, but in fact the way to think about it is that sunspots are magnetic field energy, and that magnetic field energy has been deep in the sun until during solar maximum it tends to come out, it erupts on the surface, it thermalizes, meaning it turns into the most random form of energy, which is heat, and then that heat is radiated away. And maybe a more direct way to see that is if you look at sunspots, you'll notice that there's sort of anti-sunspots around them. You don't typically see them in typical photographs, because when we expose photographs we like to show off the sunspots, and therefore we make the rest of the sun look bright, and so bright on top of bright doesn't really show very well. But if you took pictures in the H-alpha wavelength, you definitely see those extra hot regions that are surrounding sunspots. So the bottom line there is that we do see more solar radiation, we do see more solar total luminosity at sunspot maxima, and sunspot maxima has been declining for the last 60 years when global warming has been really ramping up. But now back to this study here. Whoops. Solar luminosity is on average going up, and yes, there's a 11-year sunspot cycle, and that's pretty obvious, going up and down and up and down. But on top of that, it looks like there is a trend. And now it looks like there's actually not a trend. I got to remember to hit my control key at the right moment. And then what's not shown here, but would have been really nice if it did, is because this paper, I guess, happened too early. But we're seeing the same thing here in the beginning of the 21st century. So we've had 2 very, very strong solar minima and 2 very, very weak solar maxima to begin the 21st century. So that's still there. And so that just adds import to the fact that we have been seeing a declining solar luminosity as calibrated even before we had satellite direct measurements of solar luminosity, which began about here. Just from sunspot numbers alone, you can see that we've had declining sunspot numbers exactly during the time when global warming has been really taken off. Yeah, so here's another graph showing pretty much the same thing. This one goes a little bit further. But yeah, you can see declining solar maxima and declining solar minima. And that continued during the next two cycles, which don't show on this graph. Global temperatures and the PDO, so it's not due to the ocean warming the air. The air is warming the ocean. The sun and the air are warming the ocean. And the Pacific Decadal Oscillation is sort of the largest of the oceanic thermal effects. And there is a cycle here, and it does kind of go up and down, and it does affect global temperature. So I'm not trying to tell you that the PDO doesn't affect temperature, because it certainly does. But what it doesn't do is cause an overall trend. It does not cause a trend. The trend here is due to rising CO2, rising greenhouse gases. The PDO is a cycle. It goes up and it goes down, it goes up and down. And you can see its effect here. You know, it's especially obvious here in the 50s and 60s. And obvious also around 1998 to 2010, we went into a low period there. Climate denialists tried to take advantage of that, but it's all nonsense. Look at global temperatures peaking here in 2015. Oh, excuse me, this only goes up to 2009. It peaked even more when we got to 2015, above the top of the graph here with the very strong El Nino. Anyway, it's not the PDO that's causing global warming. It's not volcanic CO2. Volcanic CO2 is a tiny fraction of what we're putting out, and you don't see any correlation here with big volcanic eruptions, or even small ones for that matter. Yeah, so here, Mount Pinatubo added 42 million tons of CO2. What did we add with our fossil fuel burning? 23,000 million tons in 1991. So, you know, that's 50 times or 200 times more. Wait a minute, 50 times more? Yeah, something like that. Anyway, it's a lot. Not even close. It's not cosmic rays, so there was somebody who tried to claim that cosmic rays might be causing global warming by seeding clouds. But in fact, there's no correlation between cosmic rays and surface temperature. Cosmic rays show no trend. Surface temperatures show a very strong trend. There's an 11-year cycle in cosmic rays because the solar magnetic field will help buffer us from the strongest cosmic rays when the sun is at solar maximum. But there's no overall trend here. It's not the urban heat island effect, so it's another climate denialist canard trying to claim that, oh, well, our cities are made of asphalt and concrete, and there's more and more cities, and therefore they're absorbing more and more heat, and that's just the only reason why temperatures are going up. It's just all these weather stations are sitting in cities. Well, that's nonsense. You didn't need to do any big studies to find that that was all total lies. All you had to do was take your sites and divvy them up between all sites, and then look at only the rural sites, only the ones that are not in cities. And then look at the thermometer trends, and what do you see? They're the same. They're exactly the same. Except for one period here, and that was during the Civil War. So why is that? I don't know. Maybe they were distracted. Certainly in the later data here, it's pretty obvious. There's no urban heat island effect. Something else, you click on that. So we've looked at over a dozen different lines of strong evidence showing that 20th century, 21st century global warming is caused by us, primarily by fossil fuel burning to make CO2. It's not the sun, it's not natural variation, it's not cosmic rays or the PDO or the El Ninos or other ocean cycles. It's humans. We are responsible, and we've known it for a long time. We went through the history of the knowledge of human-caused global warming. We've known since the papers of, well, we've certainly known that the CO2 that we are causing, and that is also raising global temperatures. We've known that since 1938 and the publication of Guy Callender. So why has there been so much denial of this? and that will be a future talk. We'll talk about the psychopathologies of climate denial. That's our next thing. We'll also talk about climate denialist tactics, and then we'll look at the future of the next 100 years, 200 years, 1,000 years, based on what we are doing today. So there's our summary. Let you study that on your own. And I'm going to go ahead and sign off. I will put this on YouTube where you can see it, and maybe others can see it as well. All right. Good evening, gang.